Next speaker is Sue, and I really didn't want to say leprosy, but I said it. Sue Lepri. I knew I would pronounce this wrong. She received a PhD 2004 from University of Michigan, powerhouse in space weather, obviously. She's an associate professor in the Department of Climate and Space Science and Engineering there. She works on studying the composition of material in the heliosphere, special interest in the origin and acceleration of solar wind. And she's going to talk to us about the coming renaissance.
I'll give you a 5-minute warning and then stand up at 1.
Thanks. Thank you so much for having me today. I'm going to talk about the planned observations for Solar Orbiter and Solar Probe. I am Deputy PI on an instrument on Solar Orbiter, so that is the thing I know the best. But I work closely with Justin Casper at the University of Michigan, and he is a PI on an instrument for Solar Probe, and so I have talked with him, and hopefully I'll provide you with a good overview of that as well. Should I say that all again? Can you hear me better now? Okay, excellent. All right. So I'm going to start off with a Renaissance painting by Antoine Caron. I think it's 1570 or something like that. Anyway, people have been fascinated, of course, by the sun for ages. And, you know, in the beginning, our best coronagraph was an eclipse. And so we've come a long way from here. But I wanted to kind of go through a little historic overview of sort of solar wind measurements. I'm mostly interested in the solar wind. And so I went back and looked through some things. And basically, at the dawn of the space age, we really did start measuring the solar wind very quickly. 1959, the Russian Luna mission that missed the moon ended up in heliocentric orbit and first detected the solar wind. Mariner 2 confirmed the presence of the solar wind as being a continuous stream of particles. And what you saw in the plots was that there was this 27-day periodicity, which related to the rotation of the sun, and you saw fast and slow streams interacting. And so that was really quite profound observations. Then we went on to Pioneer 6 and beyond, which measured the solar wind, and then, of course, Skylab, which started doing coronagraph imaging. I'm sure I've left something out, so fill in where where your memory serves you. Of course, our most recent missions, many of which are still ongoing, include ACE, Ulysses, Wind, all of which I've been involved with data analysis and doing science with that data, and then the imaging of SOHO, YOHO, RESI, Stereo, Trace, SDO, et cetera. And so we're going to build upon kind of what we learned from these missions as we move forward. I, of course, have to mention HELIOS because that was the original solar probe going into 0.29 AU, launched in the 70s. It had a suite of instruments that included a plasma experiment that measured protons, electrons, and helium, magnetometer, wave experiment, cosmic ray detector, higher energy, despite the fact that it's called low energy. For me, it's higher energy electrons and ion spectrometer that looked at kind of the below cosmic ray energy contribution of particles, and then some dust experiments. And so this probe was launched with the goal of studying the matter that existed between the sun and the Earth. And it had no imaging capabilities. And so Solar Probe and Solar Orbiter are going to go beyond this with much more sophisticated instruments and dive deeper into the science. So these early missions provided us kind of a foundation for understanding the solar wind as it's a continuous stream of charged particles that's carrying the solar magnetic field out into the heliosphere. And it has varying speeds, varying densities, different disturbances are propagating through it. We know that the heliosphere has radial and latitudinal variations, which relate to the structures on the sun and just the behavior of the solar wind. We know that coronal holes produce high-speed winds. The source of the slow wind, we still write many proposals on today. And then, of course, that coronal mass ejections have a lot of influence throughout the heliosphere and non-planetary space environments. And of course, we know that the corona is very hot, more than 1 million degrees. And so those were all, that builds the foundation for our future missions. However, these missions, even including HELIOS, were not really able to explore the region where the solar wind is being formed and accelerated, and where the heliospheric structures form. And so that's why we kind of continue to investigate this, and this is why we have Solar Orbiter and Solar Probe. So I'll talk first about Solar Orbiter, which is the thing that I'm working directly on, and then I'll go on to talk about Solar Probe. But kind of the key science for Solar Orbiter is being able to trace heliospheric structures back to the sun. And so Solar Orbiter seeks to answer the question, how does the sun create and control the heliosphere? There are 4 science objectives, and those have sub-goals that I did not put up because it basically fills an entire book. So the main science questions are how and where do the solar wind plasma magnetic field originate in the corona? How do solar transients drive heliospheric variability? And so this has to do with coronal mass ejections, flares, shocks. How do solar eruptions produce energetic particle radiation that fills the heliosphere? And then how does the solar dynamo work and drive connections between the sun and heliosphere? And so how will we do that? Well, so as I said, the key goal here is that we're able to connect in situ and remote measurements in the inner heliosphere to investigate different science and different heliospheric phenomena. So for example, if you have a flare that goes off, you can image that flare in UV and X-ray. You can then look, if you're connected to it, for the contribution of the energetic particles and energetic ions and electrons, and look for the waves that are created from the flare. And so by doing this, and Solar Orbiter will have periods where it's nearly co-rotating with the sun, hopefully we'll be able to have a very good connection to these sites, and therefore be able to more directly link the in situ observations with the events on the sun, which has always been a challenge. Ulysses gave us a view of the heliosphere out of the ecliptic. And so this squiggly line here, if you're not familiar, is a measurement of the solar wind speed from Ulysses during a solar minimum. This is the first orbit, so this would have been 1994 to 1995. The sun was very dipolar with coronal streamers near the equator, coronal holes near the poles, and so when you sampled during that fast latitude scan the solar wind, you saw a very organized structure with high-speed wind coming out from those coronal holes, and then a more variable slow wind coming from the equatorial regions. Now, during the second orbit, which would have happened in 2001, which is solar maximum, what you see is a much more disorganized corona. Now, if you look at the images, you have kind of streamers at high latitude, you have coronal holes at low latitude, and so the structure is much more complicated, and then that's also reflected in the solar wind. And so here you have fast and there is a high latitude coronal hole up here where you still see that high speed wind, but largely you have much variability in the speed of the wind, and of course all the other parameters as well. And so this is punctuated by coronal mass ejections and other shocks and things that are driven out of the sun. And so Solar Orbiter, while it's not going to go up to 80 degrees latitude, is going to go up to, say, 25 or 30 degrees, and it will provide us a view of the inner heliosphere at higher latitudes. So it's going to give us, again, a glimpse into the 3D heliosphere. The other thing is, if you look at kind of the effect of the dynamo in driving sunspots, those surface features clearly have an effect in the heliosphere, and this is the plot from Matt Owens that shows the total heliospheric flux versus time along with the sunspot number. And so there is a correlation between the presence of sunspots, which then are related to coronal mass ejections, which carry flux into the heliosphere and therefore drive up the total heliospheric flux in the magnetic in the heliosphere. And then that decays away through reconnection, and you return to some baseline value, perhaps, and then this happens over and over again as you cycle between solar minimum and solar maximum. And so trying to understand, using helioseismology, kind of what drives these variations is another goal of Solar Orbiter. Now this is a very hard to see chart, I apologize about that, but the point here is that Solar Orbiter has a set of in-situ instruments and a set of remote sensing instruments. And so there's a solar wind analyzer, which is going to, it's a suite of 3 sensors, and that's what I'm a part of. That's going to measure protons, alphas, electrons, and then heavy ions. And so there's a dedicated electron spectrometer, a proton and alpha sensor, and then the heavy ion spectrometer. There's an energetic particle detector, magnetometer, and then the waves instrument, RPW. And then there, in the remote sensing area, there's a helioseismic imager, an EUV imager, a spectral imaging of the coronal environment SPACE instrument, X-ray spectrometer, a coronagraph, and a heliospheric imager. So these things are peppered about the spacecraft. So the imaging instruments basically look through the heat shield, which is a multi-layer thermal protection system out front. And then we have a variety of, like, the magnetometer, the wave sensor, the electron sensor are on a boom, which take them far away from the contamination of the spacecraft. High gain antenna down here. And you have your heliospheric imager that's looking off to the side. And then we have the proton and alpha sensor peeking over the heat shield here, and then our heavy ion sensor peeking over the heat shield there. And they each have their own heat shield so as to protect them from the solar radiation. And although the thermal control of Solar Orbiter is a challenge, clearly the thermal control of Solar Probe is even worse. Let's see if this plays. This is just an artist rendition, some gratuitous movies of Solar Orbiter while it's out there. You can see the instruments. Oops, by clicking, I have done something. Sorry. Anyway, so you can see our instruments peeking over the edge, the instruments out on the boom, and then as you rotate around, you can see the feed-throughs for the imaging instruments. And so they have little windows that will open up. So this is the structural thermal model of Solar Orbiter in Stevenage in the UK. Getting ready for some testing. You can see kind of, there's a guy over here, sort of gives you the scale. And so we have structural thermal models of the instruments. Ready? So here is the structural thermal model of HIS, the heavy ion sensor. So what you have up top, this black thing here, is a heat shield. Up here is the electrostatic analyzer, which is going to deflect ions, basically of varying mass and charge, into the time-of-flight telescope, which is here, which uses microchannel plates and solid-state detectors to measure the velocity of particles and the total energy. And then there's an electronics box down here, which is contains a variety of components, which this is a collaboration of Southwest Research, University of Michigan, University of New Hampshire, Goddard Space Flight Center, and IRAP in Toulouse, France. And so this part here is provided entirely by the French. This is largely New Hampshire, and Goddard is providing the solid-state detectors, and then Michigan is doing some of the high-voltage power supply, and actually the entire high-voltage power supply and some of the electronics. And Southwest is integrating the entire thing. So the types of measurements that we hope to get out of HIS, that we are designing it to get, are basically measurements of all the different heavy ions in the solar wind. And so this is based on the heritage of ACE and Ulysses and plastic. And this is just a plot from Ulysses showing all these different spots are different ions. So they're different elements with different charge states. So each kind of, as you go across, that's an element. Those are iron ions ranging from low to high charge, with the most common ones being iron 10 plus and 9 plus. This is helium, helium plus over here. Then there's carbon, nitrogen, oxygen, up to I believe, 77 ions. And so at Michigan, we've been working on our routines for extracting and removing overlap from different ions. And so hopefully we will have a state-of-the-art ion identification algorithm ready for launch. And then the types of science that we look forward to doing is not only looking at different types of solar wind and tracing them to their sources, but also looking at coronal mass ejections and where energy is being imparted to heating, the plasma ionization, and acceleration. This is a plot of a period in May of, I believe it is 2005. I don't have the year on there. But anyway, so this was a cold CME. So this is a coronal mass ejection whose boundaries are marked by these red lines, the start and stop here. And then this is the plasma density, or the proton density, temperature, velocity, and the magnetic field. This is all from ACE. And then I have charge states of carbon, oxygen, and iron. And so kind of normal solar wind, normal slow wind is here with charge states of around 10 for iron. With the charge states increasing here on the y-axis, charge states of around, say, 6 for oxygen and carbon around 5. And then when you come into the CME, you see the charge state shoot up. That's kind of evidence of flare heating or connection to a reconnection site where you have enhanced ionization, perhaps through higher density or heating. And then there's also embedded within this a very cold period where you have very low charge states, which represent temperatures of around 40,000 to 100,000 degrees in the corona, which is very likely prominence plasma embedded. And so you can see that there's structure in this CME. You've got this embedded prominence. This is actually a pretty clean CME where it's not interacting with a bunch of other ones. But as we move closer and take these measurements closer in, hopefully the structures will be even more well-defined, and we'll be able to do a better job of connecting the in-situ different parts of the CME with those that are observed on the sun. Okay. I better move faster. This is just the concept of operations for the instrument. Basically, ions come in, they emit electrons as they go through a carbon foil, which starts a timer. When they hit the solid state detector, they emit electrons, which stops the timer. You get the time of flight, which relates to the velocity. You measure the total energy. You know the energy per charge from the voltage on the electrostatic analyzer, and therefore you get the mass charge of the ion. And these are all the different components. But anyway, just to showcase some of the things that we've actually fabricated, this is the solid state detector energy board, which has 32 solid state detectors. It's going to be tons of fun calibrating that. This is, I think, the start MCP assembly. And so that's an MCP, and there's basically a position-sensitive anode underneath that records the position, which relates to the incoming ion direction. These are the structural and thermal models of the 3 sensors that make up the solar wind analyzer. And this is the electron analyzer over here. Here's the proton and alpha sensor with its own heat shield that looks like a shroud over it. And this is the heavy ion sensor, and that's a microscope that's not part of it. Okay, so the orbit of Solar Orbiter is going to come out of the ecliptic. And interestingly, so the in-situ instruments are going to be operational through the entire orbit. The remote sensing instruments are only going to be operating during perihelion, plus or minus 10 days. And so you really have kind of limited time during the orbit that you're actually observing, but that's when we're going to do a lot of our key science. We've had to push our launch back due to a number of factors, and currently the launch is scheduled for October of 2018. This is the orbit for that launch date, and it involves, I think, 5 flybys of Venus, or 6 flybys of Venus, and 2 flybys of Earth, and an Earth-Venus transit. And so that will get us into about 0.28 AU. This plot is very hard to see, I apologize, but it just shows over the length of the mission. So it launched is over here in October 2018, and this is the distance to the sun. You can see how it progressively gets closer to the sun, and in 2023 it will be into that 0.28 AU. And then, here I have these dates here. So Launch is in October 2018. Cruise phase will last about 3 years. We hope to be operating we hope to be operating our sensor during that period. You'll get up to about 7 degrees inclination. And then we'll start the nominal mission phase. That'll last about 5 years. We'll get up to about 25 degrees inclination. And then the extended mission nominally will last 2 years and get up to 33 degrees. Thanks. I need to move on to Solar Probe. So why Solar Probe? Well, the goal of Solar Probe is to determine the structure and dynamics of the sun's coronal magnetic field, understand how the solar corona and solar wind are heated and accelerated, and determine what mechanisms accelerate and transport energetic particles. So in order to do this, we want to get in as close as possible, and Solar Probe is going to get into 9 solar radii and will give us a chance to observe the generation of the solar wind at its source. So to illustrate this, well, how are we going to do that? First, you're going to sample coronal particles and fields in situ. So you're actually sampling the corona. So this is a plot of the solar wind speed versus distance in a log scale. Solar orbiter, you see over here, will get into about 60 solar radii. Solar probe will get inside of 10 solar radii. And this is basically where the solar wind is still accelerating. You have a subalfanic corona, and SEPs are being accelerated. And so you'll get a chance to view these things as they're happening. The science instruments on Solar Probe are going to measure the coronal and solar wind plasmas. Justin Casper is the PI of the SWEEP, the Solar Wind Electron Alphas and Protons investigation, which is highlighted up here. They have a Faraday cup that peaks around the heat shield, and then 2 sensors back here that are also part of the instrument. We're going to measure the electric and magnetic fields, energetic particle radiation, and there's another heliospheric imager on board. This orbit is, it's supposed to launch in July of 2017, July of 2018, and we'll get to its first perihelion only a few months later at 35 solar radii. So it's going to head right in. And you can see kind of over time, this is days from launch, which isn't that helpful, but basically you can see how it's going to progressively get closer into 9.5 solar radii. Okay, so the timeline for Solar Probe, they passed their CDR in March of 2015. Launch is July 2018, and the first perihelion within 10 solar radii will be in 2024, so gotta be patient. All right, so this is an animation of the launch of Solar Probe to see how it kind of uses Venus and heads in for its closest approach to 35 solar radii. I'm sorry, yeah, that's right, 35 solar radii. And this next animation, if I can get to it, is a view of the heat shield, and you'll notice the Solar Probe cup is sticking out and glowing red. So they've tested this thing to like 1,000 degrees C, possibly 2,000, I can't quite remember. And it is able to withstand this intense radiation and still take good measurements. So this is an exciting engineering feat. This is an image of the Faraday cup being exposed at 700 degrees C, and you can see some of it's glowing. So anyway, so they've done this testing in the lab. So Solar Orbiter and Solar Probe, they'll allow us to connect in-situ observations within 10 solar radii with remote observations and also in-situ observations further out around 60 solar radii, which will give us a unique opportunity to observe the evolution of solar plasma from the corona into the inner heliosphere. You've got multi-point observations in the inner heliosphere, which will provide us a new view of structures in there. You've got an out-of-ecliptic view, which is going to give us a 3D view of the inner heliosphere, and then we'll be able to coordinate campaigns with ground-based and L1-based imagers and monitors to maximize science. There's a couple different key scenarios of alignment that we're looking forward to. So there's the case where Solar Probe and Solar Orbiter are online, so we can observe the same plasma that's propagating out at both spacecraft and look at the evolution between the two. Then we have the case where they're situated along the same field line, and then you can look at energetic particle acceleration along that line and trace it back to the sun. And then also the quadrature alignment where you have Solar Probe and Solar Orbiter at right angles, where you can image what is flying past Solar Orbiter, much like Stereo did with ACE. And of course, the heliospheric magnetic field, when it connects back to the sun, it is a very complicated connection. So we still, despite all of these advances, we'll still need models to really trace things back. I'm probably running out of time. I have a summary. So together, Solar Orbiter and Solar Probe will reveal the sources and mechanisms of the origin of the magnetic field and the solar wind. Very optimistic here. All of the questions will be answered. We'll explore the mechanisms for energetic particle acceleration and transport, and look at how the dynamics of the heliosphere relate to transients and recurrent features on the sun. And then lastly, a very optimistic video showing the orbits of Solar Probe and Solar Orbiter, and it assumed that Solar Orbiter launches next year, which is not going to happen, but it still is a fun animation to look at where they'll be in relation to each other. And so while that's playing, I can be done and take questions.
Thank you very much for a very nice presentation. I just had one comment, if I may. It looked to me, if you looked at the correlation between the sunspots and the heliospheric flux as measured in, as you produced, that the heliospheric flux was leading the sunspots. If you just naively looked at that, which is kind of curious.
I have no comment on that.
Okay. Any serious questions here? This is a big risk, but Dick?
Yes.
I'd like to know, could you remind me what the upper limit for the protons and proton energy and helium energy in the charged particle detection?
So I know for the proton and alpha sensor, the bulk plasma, it goes up to, I believe, 20 keV per E, or 20 kilovolts, basically. And then, and that would be true for the alphas as well. And then our instrument goes up to 80 keV per E. And then the energetic particle sensor takes over after that, but I can't remember what the upper limit is.
I guess maybe I was asking about the energetic.
Yeah, I can't. I'm sorry, I don't have that number.
Is
in
it
my
tens
head.
of MeV?
I think it is tens of MeV. I can look.
I just wanted to say I really enjoyed your talk. And one of the plots you showed I thought was just really exciting, where you could show the cold core of the CME coming through, which is the prominence material. As well, it was just so exciting to see the various ionization states of the actual components of the different elements that are in there. That's so exciting. Anyway, thank you very much.
Well, we can talk anytime about that.
This side of the room has been extremely quiet all morning. I don't know whether there's a sleeper's corner over here or what, but does anybody over there have a question?
Michael?
Herr Knelke, Herr Oberleutnant Knelke von der Freiburg Institute.
Last time I wanted to ask a question. You were ruling it out of time. So this wing wasn't that quiet. It was kept quiet. But I have to say that this was about 12 years ago, a very outspoken, prominent figure of your institution made a statement when my young scientists here in HAO proudly presented the first modern measurements of prominence magnetic fields, that there was really very little interest and consequence of such measurements. I remember that very vividly, and I'm glad to see that there are now people in Michigan who fully appreciate deep studies of prominences, and that they indeed have consequences for the kind of physical regime that you are studying. Now, your overview was very, very nice. The claim, and that's not your responsibility, but the claim by going out in the ecliptic by about 30 degrees to unravel the 3D heliosphere seems to me a little far-fetched.
Sure. I mean, we'd love it to go to, we'd love to have like 20 spacecraft at, all latitudes, but it's basically, my point is that it gives us a glimpse into that 3D nature which we lost when Ulysses was decommissioned. So.
Is somebody at the back have a question? No? Then last question for Joan, and then we'll thank the speakers and break.
It's just a comment. I almost always agree with Michael, but I don't actually agree on that, because I think you're going to be able to start to see those polar fields, which are really important. And I think the space weather prediction people will admit that the models of the solar wind are really in large part lacking because we don't know what's going on in the open fields and the poles. So I'm excited to see what the data look like.
Oh, thanks. Me too.
Any more comments? No? Okay, let's thank all our speakers, Sue and Sarah and Ryan.